Hello everyone, in this video we're going to look at the coordinate system that we're going to use. Now in the last video we looked at terrain generation and the algorithm that I use to generate this map. Aesthetics are not exactly smooth right now, it's just a single color, it's not very pretty. Now ultimately I'm going to have images on each tile. Now if I include some rainfall information and change the color of the tiles based on that information, we get something that is a lot nicer. I should add, this is the terrain generation algorithm that we had before. I made a couple of tweaks which are not really very important, but the purpose of me pointing this out is that there is going to be a slight change in the way this looks. So now this is the starting area. As you can see, it looks a lot better now because you have some rainfall information. Rainfall, as you can see here, is very much related to vegetation. Now obviously the actual vegetation that we can see and which creates the forests is actually also a derivative from the vegetation noise that you have here. This change is just for the aesthetics of it. It looks a lot nicer if you have those couple changes. Now you may wonder, what change is that exactly? When I'm painting the color on each tile, which later on will be painting the images for that tile, I'm simply making it darker when there is a lot of rainfall and a lot lighter when there is no rainfall or little rainfall. And it turns out when it's darker it feels like there is a lot more vegetation, and when it's lighter it feels like there is a lot more sun and everything is dried out. Now moving on, you may notice that the tiles that I used are not squared. I don't want to have squares, mainly because it doesn't look very good. At least with hexagons it looks, I don't know, smoother, and I like it better. So the question you may ask is, if you're using hexagons, it's going to be harder to compute coordinates. And indeed you are right. So the obvious choice that we could have to compute coordinates would be to use exactly the same as we had with a square system, that is to use Cartesian coordinates, so 0, 0, 0, 1, 0, 2, 0, 3 and so on this axis. And then on that axis it gets a little trickier because you have to shift with a certain offset of half the width of the hexagon on even rows, and then you get back. So we would have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. And this back and forth is actually tricky because it means that on most algorithms that we have to design for this coordinate system, we have to specify a different set of rules for even rows and for odd rows, and we have to rewrite a lot of the logic and so on, and it's pretty bad. Fortunately, we don't need to use a Cartesian coordinate system, we can use something else. For example, I don't know if you can see, but in fact those hexagons look like a projection of a cube from the diagonal. And in fact, we can use a 3D coordinate system, and in order to explain how this looks, I'd like to show you this animation. So you have a bunch of cubes in a 3D Cartesian coordinate system. But now, if you take a plane and look at all the cubes whose corner is on that plane, remove all the others, and then you take the projection of all those cubes that remained, and you get exactly what we want on the map, a hexagonal grid. Now the plane in question on which we do the projection is of equation x plus y plus z equals 0, which is even greater because that means that we don't need to store the 3 coordinates. We only need to store 2, and the other one, for example z in this case, is -x minus y, so we don't need to store this one. We can get back to it later. Now once we know we have this coordinate system, we can paint all the tiles, all the pixels of the map using 2 simple algorithms. So the basic one is the one that takes a pixel on the screen and returns the coordinate of the hexagon on which that pixel is. So for example, let's say that this pixel at the very center of this hexagon is the center of the map, so it's pixel 00 if you want. We know the relationship between this pixel and the pixel at the top left of the screen. We also know the relationship between the pixel at the top left of the screen and the pixel whose tile we want to have, for example this one. So we know the relationship between the pixel at the center of the map and this pixel, which is exactly what we compute here. And now once we have that, there's a little bit of math in order to get back to the coordinate of the hexagon. And then the thing is, we have coordinates in floating point numbers, but we want coordinates in integers. So yet again, we have a little bit more math in which we basically convert those coordinates into 3D. We round it up inside the Cartesian 3D coordinate system, and then we get back to the integer coordinates. But once that's done, we basically do have the coordinates for the hexagon that we have a pixel on. So that means that, and in this case it's very dumb, we can take each single pixel on the screen, get the tile it corresponds to, and then get the characteristics of this tile, and based on those we can select the color we want, blue for water for example, green for plains, and put them on the canvas. So in this case, and again it's not the most efficient way to do it, I put them in a typed array, and then once I've done all this and put all that into a typed array, I splash that typed array onto the canvas with all the coordinates in it with this function here, put image data. Again, that's not the most efficient way to do it because we do a lot of computation in JavaScript and it's not very optimized. I could probably optimize it, but it's hard to compete with the primitives that are written in C++ in the browser, which paint any image directly on the canvas. So that's what I did. I used images. Now let's go to master, to the latest commit, to see that in action. And it looks like this. So right now we have an image for the plains, an image for the water, and so on. Every image is a plain color. So for example, green, blue, orange, and so on. Which isn't great. I'm going to ultimately have images that show something interesting. For example, grass, hills, and actual water. But that's going to be in the future. The thing is, now that this first work is done, it's going to be a lot easier. So there are a couple more things, algorithms that I designed around the coordinate system, including some system to compute on which tiles we can go in a particular amount of time. So for example, you can go a lot slower on the mountains, on the hills, than on the plain. You also go slower in the forest. So for example here, we can go only up to there in the mountains, but you can go much farther this way. One spot that I particularly like that shows this quite well is on this island. Here it's very hard to go to this spot, which is the mountain, but it's a lot easier to go right there onto this plane. So those algorithms are also there. Again, it's not very difficult thanks to the fact that we're using this particular coordinate system, which uses 3D. For example, this algorithm shows how to get to a neighbor from a particular tile coordinate. You have the tile coordinate, you know which orientation you want to go. For example, 0 to go on the right, then 1, 2, 3, and so on. And every time, like, it's really just a +1 or -1. You have it right there, but it's easy to do it manually even. I'd like to end on an amusing note. I also made these buttons that are going to be used in the game. Let me show you how they are made. So let's inspect the element. And it's actually just SVG, as you can see here. So it's basically some SVG dumped into the HTML, and I manually draw all the lines inside with SVG paths. Obviously, when I'm going to give this to the world, I'm going to concatenate the scripts and minimize them. Right now they're not minimized at all. So yeah, thanks for watching, and see you next time.